Just got a notification. Hey, apparently we're live because I just got a notification of it. Welcome to the HTM Hackers Hangout. I'm Matt Taylor from Numenta, and it is October 6th. I'm going to mute you, Daniel. I want to welcome our new subscribers from Strange Loop. I noticed when I did a presentation on Strange Loop last week, and I got a bunch of new subscribers on our YouTube channel. So welcome, thanks for joining us. We do this HTM Hackers Hangout live once a month, and it's a Google Hangout held for our online community. Anybody's free to join in the discussion by connecting directly to the Hangout, like these people down here, or you can just connect to the video or watch the video live on YouTube and comment there. I can answer those questions. Check out more information in the video description. I put a bunch of links about everything we're going to talk about down there. If you have something specific that you'd like to discuss, or if you just want to learn more about the HTM community, please join our forum, HTM Forum. It's at discourse.numenta.org. So without further ado, I'm going to go to my agenda so we can push through that. And I'm going to share some of my screen because I do want to tell you a bit about how this last conference went, which I'm very happy with. So how do I do this? Screen one. That's not the right one. So I gave a presentation at Strange Loop, and it was the first time I've given the entire full HTM soup to nuts thing, all the way to sensory motor integration, layers and columns and all that stuff. And so I think it went really well. There's a good video of it online, and there were, let's see, where did that Twitter thing go? There was a good, right, our media page here. There it is. Picture of the crowd. So my room was big, probably the second biggest room there, aside from the actual Opera House room. And there was 400 people that could sit there, and there were standees only by the time it started. So it was a good audience. So I was really happy about that. I also had a chance to do an interview with this podcast, these guys called This Week in Machine Learning and AI. They interviewed Francisco Weber last year. They've got a bunch of different interviews of people in the AI community on their website. They put them on YouTube and they do podcasts. So I'm going to be up there because I did a video at Strange Loop with them. So that's great. The next big thing is we're having a meetup on November 3rd. So this is on the same day that I'm talking at the Open Data Science Conference in San Francisco at the airport there in that area. So we're going to have a meetup on that same night. So after that event, there'll be 3 talks. We have a community talk from Jason Toy, who's a member of our community, and he's going to talk us through something he created to help AI systems deal with 3D objects, which is very relevant to some of the stuff we're working on. And then our own Marcus Lewis, who's connected here, is going to talk about location relative to the object environment. So that's going to be a lot about the new object locations and how we're thinking about that stuff. And then Jeff will actually be the main speaker that night, and he'll give us an update on the layers and columns. That's going to be mostly just going over what's in the paper, especially good for anyone new coming into this, the new layers and columns theory. That would be a good talk for that. The other 2 are kind of more deep, I guess, more detailed. But Jeff's would be a great talk for anybody to come in and listen to. So I want to point that out. That is November 3rd at 7 p.m. and it's the Crowne Plaza, San Francisco Airport. Also, we had a nice guest blog post. If you guys are in our community, hopefully you saw this amazing demo that one of our community members, I always have a hard time saying his name, but his name's Ali. He put together this really cool thesis with this big 3D world and made an autonomous agent using HTM and did some really cool visualization. So we asked him if he would do a blog post and talk about how this worked and include some of the visualizations from his demo, and he did. So thanks to him for doing that. That was very cool. That's, I think, all that I wanted to talk about. The other thing on my agenda, I don't really have much to talk about. I am working on some this live demo of a hand touching something and the neural activations in HTM and showing like how it can resolve to an object. I'm working on this with Lewis, one of our engineers, and I'm going to try and incorporate that into one of our next HTM schools. But I don't have anything to show about that yet, but I put it on the agenda just to kind of prod me and to continue working on it. Okay, that was pretty good for 5 minutes. I got through my part of the agenda really quick. So I'd like to pass it on. Marcus, do you want to say anything about research at all?
Sure. As usual, this is pretty informal. I didn't really plan much. So yeah, a few things are going on in parallel. In some ways, we're kind of splitting the work up a little bit. The layers, the paper that we posted, it's pretty far along in the peer review process. That should be, yeah, things are going pretty well. So that's all coming along. I'm still working on the whole task of inferring the allocentric location, and that's gone quite well. Last time I did one of these little research updates, I claimed that in a couple of weeks I'm going to post a write-up showing a big idea, and I've finally finished that write-up. It's now a few months later, and so that will go on GitHub within the next few days, I would say. And we're really aiming for like getting that into a paper and such. So I'd say one of our big research focuses is calculating the allocentric location. So I'm excited to read Daniel's paper because it was timely that he pretty much proposed a solution to that as well. So I'm excited to read that paper. I would say the other big task, the big question we're considering is, there are different terms you could apply to this, but the general problem of if you're learning objects in like these modality specific cortical columns, like one that's attending to your finger and another that's focused on a particular patch of your retina and another part that's a particular patch of your cochlea, or however that all works. How is it that you can learn an object in one cortical column and then infer it in another? The general task of just how does that work? Whether you're talking about sensing an object and recognizing it, or you could talk about motor commands with you can sign your name with your foot is an example we use sometimes, and you can also set up the problem other ways. You can set it up as if you have an array of sensors that each have partial understanding, each have partial info for an object. Like no one sensor has sensed every location on the object, but all of them put together have sensed most of the locations. So how do the sensors work together? Does it require them all to learn everything somehow? Like maybe while you're sensing an object, while you're moving your hand over an object, maybe every sensor is learning everything, or maybe each is just learning little bits and somehow they still work together. And there are different ways of approaching that problem. And I would say that's like, I'd say those are the three main things on our mind, are getting the paper out, the current paper out the door and really like out there, calculating the allocentric location, and the task, you could call it transfer learning, you could call it a lot of things. We're sort of arguing over the terminology for that problem. But I would say those are the three main things we're focused on. And in addition to all that, I mean, we're always focusing on a question or a set of questions that we're trying to answer. We're also often just considering other things, looking at other people's models or applications and such, to just see if it triggers our thinking, or see if we're just having conversations with people, like talking with, right now we have a cool guy, Pierre, visiting up here in Newbert. I probably just messed up his name. And we're talking about, he presented on Rat Slam here, and we've been comparing our system to SLAM algorithms. And so we're always just kind of having conversations with people and learning from each other, and that takes up a considerable amount of our time as well. And it's a good use of time. But just if you want like a picture of what are we doing with all this time, that's another thing. So yeah, diving into these questions and just having these conversations with people.
Cool. You know, that it seems like, from my perspective anyway, I'm not doing research actively, but I try and keep up. And after the layers and columns paper, there was kind of a focus on sensory motor integration, but the idea that it exposes that sort of that modular circuit unit that's potentially constructible from layers and columns in different ways. I think there's a lot of different ways you could take that, you know, in your thinking of how, and when you're thinking about how things work. So hey, let's open it up, I guess. If any, we were talking to Daniel right earlier. So let me point out that he's on our forums. We weren't actually recording when we were talking to you earlier, so you didn't show up. But now, why don't you introduce yourself and what you've recently been working on?
Yeah. So yeah, I'm Daniel Raymond. UWR Raymond on the forums, and I've been trying to figure out this problem of generating the allocentric location signal. And actually, over the last 6 months, I started working on it about 6 months ago, and it's gone pretty fruitfully. I just recently finished a document documenting pretty much my entire theory and the details of how it's implemented in the neurons, you know. And so essentially, the general idea of the theory is that I sort of realized between two regions, egocentric and allocentric, I call them sister regions usually. They are trying to both are trying to model two of the four fundamental aspects of reality. Sort of, they're sort of objects in their abstract form, just sort of like a phone, regardless of its orientation or location, just objects. Their location in space, their orientation in space relative to themselves, sort of, and then the state or orientation of the body relative to itself. And it turns out that's actually very similar to how you think of motor commands. Motor commands are really just the change in that state. And so essentially the theory says that each egocentric or allocentric region is modeling two of these things. And actually those two help each other out a lot. For instance, in the case of orientation and object modeling, it's almost imperative to know sort of the allocentric location, which in my theory is more or less equivalent to a part of the orientation of an object. When you get a bunch of allocentric locations together, they essentially equal the orientation of an object. And the idea is that those two aspects of objects, models of objects, and the models of its orientation are very, very intrinsically linked together through layer 4 and 6A, and also through a couple other pairs of layers. And essentially, there's that sort of link between them, but there's also a link between the two sister regions themselves, between E and A, egocentric and allocentric. And so they're actually talking to each other, at least in the case of inference, they're talking to each other at the level of what I call the CT module. CT module is just a set of layers, usually, for the feed-forward part. It consists of layers 6A, 5B beta, 5B alpha, and then 5A, which has two parts that I don't really distinguish too often. So basically, these two modules within the regions are actually communicating with each other in the same way that, for instance, 4 and 6A are communicating with each other in a similar way. And essentially, it's passing back this information about orientation and the orientation of the body and its current state. And so you get this sort of communication between these two sister regions. And ultimately, what happens is the location of an object sort of helps the motor commands, which help the orientation of an object, which helps the object model, and sort of goes through this loop. And it also goes back the other way. And so, and actually there's sort of even more details between the loops that I won't get into, but essentially, turns out just the mere act of computing an allocentric location is actually only one part of the loop. There's actually all these other things that are happening that, you know, lead up to the computation of the allocentric location signal, but are actually just as important. And actually, for instance, if you think about motor commands, there's actually the exact same process going on, you know, in terms of generating the allocentric location signal, as there are inferring what the state of the body is. And actually, I'll leave it, I guess, on this. That the really sort of scary part of this theory, the really non-intuitive part, is that you technically don't even need a copy of the motor commands, actually, to compute the allocentric location signal, to compute the current state of the body, to do all the things that we would think you would need a motor command signal. It turns out that is hypothesized to not be necessary, at least for some inference. And so what turns out is that the brain might actually learn the current state of the body sort of in a very abstract form, sort of learning the current state of the body just as it needs it. And actually, what is really weird, it actually infers the current state of the body by using the orientation of objects in their location. And if you think about it, it's almost like the brain sort of predicting what motor movements you're going to do, like what actions you're going to take on some object. And it's predicting those motor movements, and those are sort of future motor movements that can be used for the computation of the allocentric location signal. And so it's a sort of recursive thing. And in the paper, I explain in detail the connections that I've found, or I guess hypothesized to a degree through my research that I've done through neuroscience papers. And so essentially, it actually says that we actually might have all the machinery we need to actually make two of these sister regions, at least to feed forward portions of them. We actually have, for instance, an inference algorithm. You know, the Numenta just recently published a paper talking about how you can have sensory motor inference and temporal inference in the same set of cells, and I think that's exactly right. That layer 4 is actually doing both temporal and sensory motor. And along with 6A as well. But also, it turns out you need this thing, you know, a pooling layer, right? I guess a temporal pooling layer is what Numenta called it. It's this thing that is actually, if you think about it, the difference between an inference layer and a pooling layer, or a temporal pooling layer, is actually merely the cells which they connect, the temporally organized cells which they connect to. So for instance, in an inference layer, specifically with the sort of temporal inference, it's connecting to the t-1 cells, you know, the cells from the previous time step. Now, what I've hypothesized, the neural mechanism for a temporal pooling layer, I haven't seen this in Numenta's writings yet, but I've hypothesized that it's maybe connecting to the currently active cells, which actually create the pooling effect. And it uses this thing which I've tentatively called I think it's intersection of the, actually no, it's competitive uptake ion inhibition, I think. Or, you know, something like that, where essentially the cells are actually, they're competing for the uptake of sodium, right? And in doing so, the ones which have you know, been depolarized currently dominate and sort of become active prior to, and you know, thus sort of inhibit the other cells. And so that's happening in the pooling layer and also in the inference layer. Except the difference between the inference and the pooling is merely the fact that the pooling connects with currently active cells. And so it tries to currently inhibit essentially all the other cells that are getting maybe proximal input, but don't have distal connections, you see. And so just by the mere fact that some cells develop distal connections, which if you think about it represents the object itself as the distal connections within a temporal pooling layer, that set of distal connections sort of primes those set of cells that have those connections to always be active when, you know, a set of feed-forward inputs are given from an inference layer. And of course, that's the goal of the temporal pooler, is to do that. And so that's sort of the other small part of the small portion of the theory, which is talked about in the paper. And so the inference layer, that's all said and done. The pooling layer, that's all mainly hypothesized, said and done. I've also sort of thought that those are actually the only two things you need to put into code, essentially, to actually have in the cortex to be able to make a full cortex. And so there's only two types, you know, that's the hypothesis. And so I've been actually trying to create a pooling layer of my own along with an inference layer, which of course the code is already sort of established for that. But I've been trying to make a pooling layer in code myself, and it's coming along in terms of the pseudocode for it. I think Numenta actually has a pooling layer already made. I've looked at the code. I don't know if it's exactly biologically, sort of biologically accurate, at least the code that I saw. But this way of thinking about it might actually make the problem simpler, because it's virtually going to be almost identical to the previous code. It's just that you're connecting to, to the inference code. It's just that you're connecting to currently active cells, which really makes the big difference.
Mm.
And so I've been working on that in hopes of actually testing my theory, testing the generation of the allocentric location signal theory in a whole, trying to make the two sister regions and also code in the connections which I have hypothesized in the paper. Now, I guess the little final other thing is that this is sort of the weird thing I came across, that you actually don't even need connections.
Say that again. You don't need what?
Oh, the distal connections.
Okay, so you cut out for a second. So thank you.
Yeah, of course. So when you're actually modeling it in the code, just like a temporal inference layer would not have any of its distal connections already decided for, it would learn those over time based on the sensory input. I think that's how the E and A regions are actually communicating with each other. Distally, at least, they have to learn those connections. There's essentially going to be a potential connectivity between certain layers here and certain layers here. But yeah, exact connections of whether I'm connecting to this layer within the E region or this layer within the U region, that's all sort of learned, I think. What is necessary, though, is the apical connections, which there are apical. Through my research, I've found that there are apical connections between these two regions that sort of determine the general flow of the real proximal flow of information. And I say proximal, not that it's actually proximal, in that it's not actually synapsing to the proximal inputs, but it's causing a action potential, or at least in the paper, I hypothesized that essentially distal and apical inputs concurrently, and there's evidence for this, I think, that concurrency of those two types of inputs, which by themselves don't actually cause an action potential, together they actually cause an action potential in the cell, which is maybe to the same potency as a proximal input. Actually. And so essentially the apical connections are very important because they sort of prune the activity of where information is being directed in terms of on a layer by layer basis between the two regions.
Hmm.
So that's a little minute overview of.
I've got some studying to do.
Yeah. But yeah, I love to talk about it more. Maybe whenever you have time.
Yeah.
Thanks, Daniel. So yeah, we appreciate your contribution to the well of ideas we have going on here.
I love contributing.
Hey, Glenn, nice to see you. Do you have anything?
Hey. Oh, hold on.
I hear you.
Can you hear me now?
I could hear you before.
Oh, no. Okay, now can you hear me?
I can still hear you.
Okay. That's all right. There's still a line through my microphone on my side. I'm working on two projects, and it's too early to talk about them, but I have been working on them for a long time. One is I want to know what HTM feels like. I'm beholden to the psychology side, so everything I work with functional systems, and I want to work towards where HTM is. So functional system meaning online humans, and I'm trying to reach out to the center. So what I'm trying to get to the point where I can propose a model to you guys from the psychology side and see if we can meet in the middle somehow. The second thing I'm working on is what is the basal ganglia companion theory to HTM? And that's coming along super well, and I love it, but it's also way too early to talk about it. But those are my two projects. Someday they will be done, and then I will be super excited to share them.
Great. Thanks for the update. Jacob, do you have anything you want to share? Sorry, I can't hear you. It's going to have to be a no, I think. And there's someone I don't recognize, Samuel O, with no video. Thanks for joining us. I assume you just want to be silent, but you can unmute if you have anything to say. And in the meantime, we will wrap up because we've run out of time. One more chance for anybody to bring anything up before we wrap up. All right, that's good enough for me. Thanks for joining HTM Hackers Hangout. We'll see you in a month or on the forums. Take care, everybody.